Okay, we looked at two distributed loads so far. We looked at a rectangular distributed load and we looked at a triangular distributed load. And basically what we did when we were trying to calculate the force, the equivalent force that this distributed load is we took the 100 pounds per foot and we multiplied it by the 4-foot length. So we basically took the W and multiplied it by the length. And that was what the force is. Let's say we have a problem that isn't clean. It isn't a rectangle or it isn't a triangle. It's some weird distributed load on a beam. This is still denoted as W, and this is still my length. And if I want to find out what this force is, how am I going to do that? Well, going back to this problem, we multiplied the 100 by 4 because that gave us the area of this. And in calculating what this point load was, we took 1/2 the base times the height because we were looking at an area of a triangle. If I'm trying to find the area of this, what's another way of finding area? Integration, right? So in a weird shape that we don't know the centroid and we don't know the force, we need to do integration. Where with these two, we don't. But let's derive how we're going to do the integration. Whenever you do integration, right, you know from math and physics, you're taking a little slice of this. So I'm taking df is equal to dw times the length. And let's call this, yeah, the length, but we're going to call it x. Okay? So I'm going to change this. The derivative of the force is equal to the derivative of the w times x. But I want to calculate what the force is, and I'm going to integrate. So in the end, the force is equal to the integration of w dx. You see that? Integrating a derivative gives me f. And then I want to find what w is constant, but it's this. That's the small piece. So I'm going to say w dx. So if I go over here, it would be the force is equal to the integration of w dx. So should we do one? We're going to do one in a little bit. Let's just do this. So I have my my pictures here already, but let's put my y-axis and my x-axis, and here is my distributed load. It's 100 pounds per foot. It's spread over 4 feet. So my force is going to be equal to the integration of w dx. The integration from 0 to 4 of w, which is 100, dx. So what's f going to turn out to be? This is 100x from 0 to 4, and it comes out to be 400 pounds. So of course, when it's a shape other than these guys, well, first of all, if it's a rectangular triangle shape, you never have to do integration at all. The only time you have to do integration is when it's a funky shape, and in that case, they have to give you the equation. You need to get the equation of whatever this curve happens to be. But let's go one more step before we do an example. How do you think I would find, well, sorry, let me back up. You were able to calculate the area here, and you also knew where the centroid is of a rectangle. So you were able to get the force, the equivalent force, and its location. Its equivalent force location problem. Well, not only do we want to find the force here, we also want to find what that x distance is. Can you figure out how we would find the x distance? What else do we need? We know that x, don't we, the perpendicular distance is equal to the absolute value of the moment divided by the absolute value of the force. So we need to find the moment. And what do we know about moments? Moments are forces times distances. If it's forces times distances, doesn't it make sense that the moment is equal, in terms of integration, the integration of wx dx? So how did I go from this integration of the force to this? What did I do? The only thing I did is added the x in there. Doesn't it make sense? Because a moment is a force times a distance. So once I calculate the force by integration, and once I calculate the moment by integration, can I then solve for my centroid? I just divide the moment by the force.